Hello, everyone. This is lesson 7. Um, I haven't been recording many lessons lately, but hopefully I'll do 2 in succession today. Ionization pattern, particularly, they usually ask maybe period 2, ionization pattern, what happens? And but more importantly, anomalies. The anomalies that we have in between certain elements in period 2. Remember, we used ionization pattern to discuss the existence of orbitals in shells a couple of lessons back. So just to reiterate, ionization is the energy that is required, or rather the first ionization is the energy that is required to remove 1 mole of electrons from 1 mole of elements in their gaseous state. So if you want to ionize, say, sodium is a metal. So first you have to heat it up until 1 mole of it turns into its gaseous state. And then after you've done that, you have to spend more energy to draw out, to take out 1 mole of electrons. It was, in essence, 1 electron from each atom in its gaseous state. Remember what we're talking about when we talk about ionization of metals, all right? It's taking electrons out. As you know, as we go from left to right, the number of protons in the nucleus increase, doesn't it? So lithium is atomic number 3, beryllium 4, boron 5. So they have, for the same number of shells, they have more protons in the nucleus. So as a consequence, they draw electrons closer to themselves, because the nucleus has got a high charge density. It's more positive, there are more protons in there. So it means that as you go from left to right, they take electrons closer and closer, the outer shell electrons are closer to the nucleus. Now imagine if our task is to go and take electrons away from these guys. Well, obviously, as you go from left, which are the giants of the periodic table, group 1, lithium, sodium, potassium, those lot. As you go towards the right of each period, the atoms become smaller, and therefore the amount of energy you have to spend to take these electrons out, because of the stronger nuclear attraction, becomes less and less. The distance between them becomes less and less, and therefore the amount of energy you have to spend to take the electrons out becomes greater. So if in the exam they ask you what happens to the ionization pattern as we go across each period, you say it is one of ascending. So all you have to do is, so for example, your y-axis is the energy, and then you just draw something like that, roughly speaking. And of course, you list all the elements down here from lithium all the way to neon, and then that's energy in kilojoules per mole. And all you have to say is that it is ascending. But that is a 1-mark question. You understand? Don't expect anything more. Now, what we are doing now, if I get rid of that, and perhaps use a slightly darker color so it becomes more visible to all of you, is, yeah, okay, we understand that. The whole thing makes sense. This ascending trend, ionization, due to the elements becoming smaller and smaller, the electrons in the outer shell getting closer and closer to the ever more positive nucleus, because it's got more protons in it. That is quite obvious. But then whenever in chemistry or in sciences we come to anomalies, it means you understand all of that, but then you understand something on top of that, when something doesn't really follow the trend that we expected. Now, in this lesson, I'm trying to explain to you as to between which elements and why. I've written the electronic configuration of the elements, so I did not write the 1s2, the first shell for each of them. But imagine all of them is 1s2, 2s2, 1s2, 2s2, 2p1, etc., etc. Now, well, obviously, let's put a line there. Let's change that color to black. Okay, so that's lithium, and then that is beryllium, boron, then you have carbon, then you have nitrogen, then you have oxygen, then you have fluorine, and then neon. Neon. And then the y-axis is just energy. I'm not going to write any numbers there, but the unit is kilojoules per mole, right? Kilojoules per mole. Now, obviously, lithium being the giant of the period, and with only 3 protons in the nucleus, its nuclear charge is not going to be that great, is it? So let's put a different color there. So let's say it would be somewhere here, right? It would be somewhere there. I don't know what this does now. Beryllium is 1s2, 2s2. The second shell has already started, right? And then the orbital, the s orbital in the second shell is now full. And as you will know, full orbitals will be relatively stable, right? So let's say beryllium, you have to spend more energy throwing an electron out of beryllium. Sorry, I did not write the E there. So that is our good friend beryllium. But when it comes to boron, something strange happens. Boron is 1s2, 2s2, 2p1. Now, of the p orbitals that are 3, and there are 6 electrons in the p orbitals, 2px, 2py, 2pz, this boron has only got 1 electron in the p orbital. Now, you have to consider whether you require more energy to remove a single electron from the p orbital, or to go and mess around with the 2s2 orbital, which is full and stable. And it will require less energy to remove the 2p1, right, from boron, than to go and disturb one of the electrons and take an electron out of the 2s. So for the first time, if I may use a different color so it becomes slightly more visible, so it actually requires less energy to ionize boron. So that's your first anomaly. Then with the other ones, it follows the trend as we were expecting. So this is more, and that is more. You see one of ascending going up. And then it comes to oxygen. Oxygen electronic configuration is 1s2, 2s2, 2px2, 2py1, and 2pz1. So in the p orbital, it's got 2 electrons in there, 1 there and 1 there, right? Now let's compare that with nitrogen, that in the p orbitals, they are just half full, 2p3. To remove one of the electrons from the 2px2 of oxygen would require less energy, because when you remove it, it's still half filled and stable. But if you go in nitrogen and try to remove one of the electrons from the 2p3 of nitrogen, you are actually overcoming and destabilizing the stability, the half-filled stability of the p orbitals in nitrogen. And therefore, it will require more energy to go and take 1 electron out of nitrogen p orbitals than to take the 4th one from oxygen. So with oxygen, it drops again, yeah, compared to nitrogen. So basically, what are we doing? We are comparing oxygen with nitrogen. That's where the anomaly takes place with oxygen in group 6. And then we are comparing beryllium with boron, and boron in group 3, which drops again. So the anomalies really are in group 3 and in group 6. And the rest of them, they just carry on as they would. Fluorine, of course, atomic number 9, 9 protons in a very, very highly charged, and you want to go in there and take an electron out, well, you've got a job on your hand. And of course, with neon, it's 1s2, 2s2, 2p6. The p orbitals, in fact, the second shell is full. The s orbital and the p orbital are totally full, and when they are full, they are extremely stable, and they don't want to lose their electrons. And furthermore, they have more protons in the nucleus. These electrons, random, are attracted like mad, and therefore you have a job in order to actually remove them. It's enormously difficult to remove them. So in order to explain the anomalies, which is the next step up, than just talk about trends in ionization, we need to know about electronic configuration that hopefully you've already learned. And now the significance of this electronic configuration, the idea of how stable certain orbitals are, the fact that half-filled orbitals, fully filled orbitals tend to be stable, particularly, of course, fully filled orbitals, and then the comparison. When you come to explain these things, say on exam paper, as chemists, you have to be very specific, talk about which orbitals we're talking about if you're ever asked. You have to be very specific, use terminologies that are unique to our subjects. Okay? I try to make these lessons as short as possible so you don't get too bored. All right? In the next lesson, lesson 8, I'll be talking about shapes of simple molecules. And then in those lessons, which will follow this immediately, again, we'll see the role that electronic configuration play. Okay? Well, thank you very much.